like to say welcome, and it's a great honour to have this opportunity to discuss with you the exciting events of the last few years and what that will mean for the future of this new field of gravitational wave astronomy. So my name is Martin Hendry. I chair the Education and Public Outreach Group for the LIGO Scientific Collaboration, and it's my great pleasure to be here at this meeting on multi-messenger astronomy in the era of LIGO India. So perhaps we might begin, if you could tell us a little about your perspectives on how we've reached this point, going from the idea of LIGO India, the concept of LIGO India, to now being on the brink of beginning the project properly.
Yeah, so it has been a very exciting time. So basically, scientifically, there are two observatories in the United States and one in Europe to detect gravitational waves and look at the universe through this new window that has been provided by gravitational waves. But all these observatories are really in the northern hemisphere. And for some time now, the idea was that if there was another observatory in the southern, at a different latitude, so in the southern hemisphere or close to the equator, then one would actually get much more science, because with these observatories, one can then localize the source of gravitational waves, where the waves are coming from, and therefore learn much more. So initially the idea was that this observatory would be put in Australia, but in 2011 or so it became clear that the funding for that would not be available from the Australian government. And it just turned out that at that time I was in India for a scientific committee meeting, advisory committee meeting at IUCAA. And then I received this news from that deputy director of the National Science Foundation, Ed Seidel. And so we started a preliminary discussion about whether, in fact, India could really jump in and substitute for Australia. And fortunately, the chairman of the board for IUCAA was Anil Kakodkar, and he is a very distinguished scientist and holds many responsible science policy positions. And he got excited with this idea because it really serves many different purposes at the same time. First of all, there's fundamental science. I mean, one is really testing something about Einstein's theory of general relativity, which is considered as being the purest, most beautiful science. But it also teaches us a lot about the universe as a whole. In addition to that, having a facility like this, of this magnitude, which is called a mega project in Indian terminology, on the Indian soil, was very attractive to these policymakers, because that means that there will be a lot of upgrading of industry, because we'll need many components coming from industry, and it would provide really very good ground for training and getting human resources, so to say, at the first level, at the best level. As we know, LIGO detectors are among the most sensitive in the world, and therefore one really uses forefront technology, and therefore this would also push the frontier of technology within India. So all these factors came together. There was very energetic contributions from Bala Iyer, from Tarun Saudip, and Ajit Kembavi at IUCAA. And therefore, we pursued this with the policymakers in the central government, Mr. Kasturi Rangan, and who was then in the Planning Commission, and the Prime Minister's scientific advisor, Mr. Chidambaram. And then there was excitement about this whole idea, and therefore the ball started rolling. It has taken some time, but the discovery of the gravitational waves, the first event, really sparks a great interest all over the country, including in the central cabinet, and therefore this project was then approved. And as you say, it's really exciting that just last week we got LIGO India has got the clearance for the site and the environmental examination. It has passed all those tests, so now really groundbreaking can begin. And therefore it is truly exciting time. It's been a long journey, a lot of hard work by many Indian institutions. IUCAA the Institute for Plasma Research, IPR in Ahmedabad, and RRCAT, the Raja Ramanna Center for Advanced Technology. Scientists have worked very hard for this, and so I'm glad that this is really now coming to fruition.
Absolutely, we're all glad about that, and it's a great microcosm of, I suppose, what has been seen on the global stage as well as a project that has required real dedication by thousands of scientists around the world, not just for a few years, but literally for decades, yes, to see through from the initial conception to making it happen. So that's the kind of the politics of it, and it illustrates that, you know, being in the right place at the right time to make that push back in 2011 was a crucial contribution from you personally, for which we are very appreciative. But let's talk about the science that we're going to do with gravitational wave detectors like LIGO India, indeed the science we've already done. So you mentioned that this is a way of probing really fundamental aspects of science. That's Einstein's general theory of relativity. So for many of our followers, they might be a little familiar with what GR is all about, but let's go back to the basics of that. How does general relativity differ from our picture of gravity from Isaac Newton, and how does that lead to the prediction of gravitational waves?
Indeed, I mean, I think most of people know that the first theory of gravity we had was from Newton, and Newton introduced both certain clear notions of space and time, what space and time, through his postulates in this very, very celebrated book, the Principia Mathematica, and also introduced the universal law of gravitation. And the sort of the unbelievable thing was the most impressive, dazzling leap Newton took was to say that gravity is universal. That is to say, the force that actually makes the apple fall down from a tree is the same as the moon, as the force that makes the moon go around the Earth. So this is really kind of staggering that, you know, that this extending the reach, making everything universal. The only difference between the apple and the moon are really their initial conditions, the initial position and the initial velocity. The law of motion is the same. So because of this staggering, astonishing universality, the Newton's theory of gravity really reigned supreme until for close to 3 centuries.
Yes.
And then finally the Einstein's theory of relativity was born. So how did this come about, and what is the difference between the two? Well, in Einstein's theory of gravity, general relativity is a theory of gravity. It's a better theory than Newtonian gravity. But it also is very different in that gravity is absorbed in the very geometry of space and time. We are all used to thinking of space being just out there, sitting there, nothing happening, and providing us a stage on which things happen that we describe. Various planets move, various things happen, that all happens in space. And similarly, so to say, time just marches along. It cannot be affected. It is just the same everywhere. Whereas in Einstein's theory, space and time are not so passive. They can be acted upon and they act back. So in some ways, they really join matter. It is like they are not fundamentally on any different footing than the celestial bodies or these chairs that we are sitting on, or you and me, which can be acted upon and which react. So it's a very profound paradigm shift in which space and time becomes a physical entity rather than just being a background that is given to us. And then what happens is that massive bodies actually bend the geometry of space and time. And other particles, other bodies move in this bent geometry. So for example, we all think of in Newtonian gravity that we've got a central sun which exerts a force on Earth, and that is why the Earth goes around the sun. In Einstein's theory, his sun is a very massive body, so it bends space and time geometry around it, and Earth moves in this bent geometry. Really, in this bent geometry, Earth is trying to go as straight as it can. But because the geometry itself is bent, then from older Newtonian perspective, it would look like the Earth is actually following a curved geometry, a curved path. So It's a very radical idea in which the gravitational force is absorbed in the very nature of space and time. Just for the people who might say, well, this is all very exotic, it may be good for black holes and so on, let me just say that this idea is fundamental in our everyday life. All of us have, for example, a cell phone. And the cell phone has a GPS, global positioning satellite system working on it. That is what tells you where you are, that tells you the Google Maps and make it all work. But the satellite, the clocks tick at a different rate than they click on Earth because space-time is bent differently and because the clocks are moving relative to us. These are effects of relativity. And if these effects were not taken into account, then our GPS system would fail. It's quite astonishing. If you can do the detailed calculation and show that in 2 minutes, the pilots will not be able to land their airplane on the runway because the error would grow more than 10 meters and then they would not be able. So general relativity, even though it is so pristine and so pure and so abstract and so mathematical, it has practical consequences for our everyday life. And this is kind of a basic lesson that one should all keep in mind, namely that fundamental laws of science always matter. At some stage they matter. May not matter immediately, but at some stage they matter.
So you mentioned that general relativity is a better theory. I suppose, based on what you've been saying, and indeed my own perspective on this too, there's two kind of qualitatively different respects in which one might say that it's a better theory. Firstly, the predictions are more precise, a more accurate description of how the universe really is. But would you say that it also, on a kind of philosophical level, is a better theory as well, as giving a better framework to think of how gravity actually works?
Yes, I mean, there is a conceptual tightness in general relativity. The idea that this force is really absorbed in the geometry of space-time. And therefore, and that happens because of universality of gravity. Other forces are not universal. For example, electromagnetic force is different between positively and negatively charged particles. Or there is no electromagnetic force if the particle has no charge at all. But gravitational force is the same for everything. And that is why it could be absorbed in the geometry of space and time. So it's really conceptually tight and mathematically elegant and physically so precise theory. And therefore it really is very pristine experience to work in general relativity.
So we have this precise set of predictions and this very elegant framework. How does that lead to gravitational waves?
Right. So as I said before, the gravitational force is really absorbed in the very geometry of space and time. So space and time is bent. Now, for quite some time we have known that if you have two electric charges, so I'm making a slight detour. So if I have two electric charges, positive and negative, and if they're oscillating, so what one says is that their dipole moment, that's a term one uses, that changes in time, then that emits electromagnetic waves. And that is how, in fact, for example, the radio works. The antenna actually has this dipole moment changing, it sends out radio waves, those are electromagnetic waves. In gravity, it is similar, qualitatively. If you have two objects which are moving around each other, then one says technically the quadrupole moment, that's just a technical term, it's kind of a deformed sphere, has a quadrupole moment. The quadrupole moment of the system changes in time. And when that happens, there are gravitational waves produced. That is to say, that means that as these objects are moving around each other, there are ripples in the geometry of space and time which propagate at speed of light and they propagate away. And these ripples are gravitational waves. So it's basically, if you have a stationary object, then the gravitational field is bent, but there are no ripples on it. But if two objects start moving around each other, then this motion creates some ripples. And so it's a very beautiful idea that we are literally measuring ripples in the very geometry of space and time.
So those gravitational waves are associated with the changes in that curvature then. As you said, if you have a static massive object, you still have the bent space-time, but it isn't changing. So why did it take us 100 years to detect them then, if we have this wonderful, elegant theory?
So Actually, there are two answers, two fronts. First of all, there was a lot of confusion, and which is what sounds very surprising today, but there was a lot of confusion on reality of gravitational waves.
Yeah.
And surprisingly, Einstein himself contributed a little bit to this confusion
Yeah.
that people may want to know. Just a couple of years after he discovered general relativity, which was in 1915, Einstein found that, in fact, in some approximations, there would be these gravitational waves, which are analogs of the electromagnetic waves. But then 20 years later, 1936, he changed his mind and thought that gravitational waves that he had found before were artifacts of the approximations that he had made. And if you looked at the complete theory, then in the complete theory, there would not be gravitational waves. Theory is sufficiently mathematically complicated. These are ripples in the geometry of space and time, and therefore we have to sort of, in a correct manner, sort of say what the background is and what the ripples on the background are. And this is not mathematically trivial matter.
Separating those two is not so straightforward. Yes.
Exactly. Separating the ripples from the background is not straightforward. And that is why there was some confusion. So until about 1960s, so it is really, we're talking about 50 years after the discovery of general relativity, there was still a debate whether gravitational waves exist. But several researchers in England, particularly Hiram Bondi, Roger Penrose, Ray Sachs, who was in that group, he's an American, but he was in that group, Ted Newman in America, they then found a way to separate the background from these ripples and say that gravitational waves exist. They calculate the energy they carry, the momentum they carry, and so on. So they really establish the physical nature of gravitational waves. Now the second question about actually seeing them, actually receiving them, actually measuring them.
Yes.
So what happens is basically that it's a quirk of nature that the gravitational force between two objects is very small compared to electromagnetic force between two objects, for example.
Yes.
For example, if I have an electron and a proton, the electric force between them is about 10 to the power 40. So 10 followed by 40 zeros stronger than the gravitational force.
Yes.
And so it's true that these moving objects actually produce these gravitational waves which are going out. But these waves are extremely, extremely weak. And therefore you need very sophisticated technology to actually measure these gravitational waves. But one analogy is to talk about kind of elasticity. Everybody is aware of elastic bands, like rubber bands, they have some elasticity. And there is a Young's modulus which says how much pressure, how much force per unit area you need to exert to create certain strain.
Yes.
And that Young's modulus, for example, can be calculated for rubber, can be calculated for steel, can be calculated for space-time. Space-time also has this Young's modulus.
Yes.
And at the frequencies that we can realistically measure gravitational waves, that Young's modulus is something like 10 to the power 24, times larger than the Young's modulus for a rubber band. So it's extremely difficult to measure this stretching. It's difficult to stretch space-time. That's why gravitational waves are so weak, and then it is difficult to measure.
I mean, that's interesting because I suppose we often use an analogy for space-time as like a rubber sheet. But I suppose what you're saying is that rubber sheet is incredibly stiff.
It's extremely stiff.
In fact, the bend in the rubber sheet that we can see as the analogy in reality is incredibly small.
Incredibly small. And then what we're measuring now with gravitational waves are changes in that. So that's even smaller.
Even smaller.
And so finally one had to build these instruments, which are among the most sensitive instruments ever built in the human history, which can actually measure changes in lengths between two objects, which are smaller than a proton radius, which is completely mind-boggling. Proton is a subatomic particle. It resides in the nucleus of an atom, so it's even much smaller than the nucleus, and one can actually, one needed this. Or if you like, if you look at the signal that is coming from the next star, which is Alpha Centaurus, if you look at the distance between that to that star, then the change that we are able to measure is really a human hair.
Yeah.
So it's really incredibly accurate measurements that apparatus that we needed, and it just took a long time for technology to catch up.
Yeah.
And now we are here, and we found this extremely exciting results in just the last couple of years.
Yes. So you mentioned at the beginning that one of the exciting possibilities that LIGO India will present us with is the ability to localize on the sky better where the gravitational waves are coming from. So we'll come back to that in a moment, but perhaps just before we do, you could tell us a little bit about what we've learned so far and how you personally sort of responded to those discoveries. I mean, I spent several weeks just walking around with a smile on my face because of the sheer excitement of being part of that. So I imagine it must have been the same for you.
Yeah, I mean, I was always convinced that we will see these gravitational waves, but there was kind of a little bit of despair even in some of the younger but leading people working on that, namely, will technology catch up? Will nature be kind enough to give us signals of the appropriate strength that the technology can actually measure? So these were really not clear at all. And maybe people thought, as you said, people had already spent decades, and everyone has to spend more decades before one can actually see this effect. So it was not clear. But for me personally, since you asked, I was absolutely sure that we will see these waves. Exactly when, of course, we did not know.
Yes.
So when the announcement came, it was a total great surprise. And I mean, surprise in the sense that, in fact, the technology has reached that stage.
Yes.
Also, maybe people listening to this interview don't know, but it's amazing that the first signal came the day that the advanced version of the LIGO interferometer was turned on the same day. So nature was very kind to us to send us an event. But just again, for these people to see what is happening, this event was triggered by two black holes going around each other and merging 1 billion years ago. So that was the time when Earth was spawning the first molecular life. It was really a long time ago, and those waves have been traveling for 1 billion years, and now they arrive at Earth, and we had the sensitive instruments to measure them. So it was a total euphoria. Furthermore, from a purely scientific point of view, one learned many new things. Not only direct detection of gravitational waves, so they exist, but also the black holes which produce them had masses much larger than any people had expected. People thought that those masses would be roughly about 5 times the mass of the Sun. But here we're talking about masses which are 30 times the mass of the Sun, and we didn't know that such black holes existed. So existence of proof of existence of black holes, existence of this kind of black holes, and gravitational waves all came together in the very first discovery.
Yes, indeed. So that's more than 3 years ago now, but we didn't stop there. So what else have we discovered since then?
Right. So by now there have been 11 such events that have been seen. 10 of them are mergers of binary black holes. That is to say, two black holes which go around each other. As they go around each other, they emit gravitational waves, and therefore they lose energy, so they go in tighter and tighter orbits, and finally they merge. And 10 of those events are this. And one event, which is really spectacular, is that we have extremely dense stars, which are called neutron stars. How dense? Well, the radius is about 10 kilometers, but the mass is bigger than the mass of our Sun. So imagine the mass of our Sun compressing down to a radius of 10 kilometers. So the density is really extremely high. It's a nuclear density. So basically a spoonful of that matter would weigh a ton. So it's really extremely dense situation, and these stars also were going around, losing the energy through gravitational waves, and finally they collapsed, and then they actually merged and formed ultimately a black hole. But in this process, because these are stars, they have interesting matter in them, so huge amounts of matter was ejected. So these stars, as I said, each of them was larger than the mass of the Sun. But interestingly, what they ejected is very amusing. What they ejected are heavy elements, and by some estimates, as much as 2 Earth masses of gold was emitted, and 3 Earth masses of platinum was emitted up here. So that's really quite amazing that such things happen. And now people are slowly coming around to the viewpoint that most of the heavy elements like gold, plutonium, they are actually made in this neutron star collisions up here. So we have learned huge amount about nature just with these few events.
So that was a spectacular discovery that I suppose even after the black hole discoveries caught the world's attention again. And I guess one of the ways that came about was the involvement not just of gravitational wave observations, but also observations across the entire electromagnetic spectrum. And I think that brings us back to one of the points you said near the beginning, as I said we would return to that the ability to detect that electromagnetic radiation was greatly enhanced because the gravitational wave detectors could localize the position of this neutron star merger very precisely on the sky, I think to about 30 square degrees. And that will, as I understand, become even more impressive with the addition of LIGO India and indeed another detector, Kagra, in Japan over the next coming years to give us a network of what we refer to as the Big Five, the LIGO detectors in the US and then in India, plus Virgo in Italy, and then Kagra. So what kind of science do you think we might do with that network of detectors and the enhanced localization capabilities it will offer?
So what LIGO has done, or what gravitational waves have done, is really opened a new window on the universe. Right? So far, all our knowledge about the universe came through electromagnetic waves. The telescopes that we have are various forms of light. That can be visible light, that can be radio waves, very long wavelength light, or that can be X-rays and gamma rays, very short wavelength light. So, but it is all one force of nature. What gravitational waves have done is shown that a second force of nature, namely the gravitational force, can also send signals and can also send us images of what happens in the universe. And the one great strength of this is that when light or photons or this electromagnetic radiation that is emitted far away, when it reaches to us, in the meanwhile it gets scattered a lot and it loses a lot of memory of the initial event. Whereas gravitational waves, when they reach us, they are not scattered much at all. Again, because of what we discussed before,
the stiffness of
the interaction is very weak. Newton's constant is so small. So they really bring us a very faithful image of what really happened there. So for example, we're going to learn much more about how the black holes deform, how they merge. When they first merge, the geometry is very complicated, but they soon settle down. But we're also going to learn a lot about the rest of physics. So basically, there are four forces of nature. There's gravity, we have the window of gravitational waves. We have electromagnetic force, which is really the light and the radio waves and the X-rays and such things. Then we have got so-called weak force. And this weak force is responsible for radioactive decays. And that weak force is transmitted through particles which are called neutrinos. They are also very light particles, and they also have very little interaction with anything else. And finally, we have carriers of strong force, which is called the strong interactions, and these are basically atomic nuclei, the constituents of them, protons, protons, neutrons, and other particles, and then constituents of them themselves, and so on. And now what's happened is that all of the worlds, there are observatories which are looking at the universe through all fundamental forces of nature. This is the first time that will have happened in the last 20, 30 years, or in fact with LIGO joining, it's really in the last 3 years that we can look at nature using all four fundamental forces of nature. So there is, because of this, there is truly what is called multi-messenger astronomy or astrophysics. Namely, we got gravitational messenger, electromagnetic messengers, neutrinos, and cosmic rays, which are the strong force messengers. And they bring us different kind of information. So we can now look at the universe in a holistic way that we could never. So we're really extremely lucky. For the first time in the human history, we can look at the universe using all four fundamental forces of nature. So in concrete terms, your question, what are we going to learn? Well, for example, we don't know much about what happens to atomic nuclei in extremely strong densities, extremely high densities. Technically, it is called the equation of state. How does the pressure change with density? We don't know that because on Earth, even with the most powerful accelerators, we cannot create such configurations as nature creates in stars
like these, yes.
in this. And so we're going to learn a lot about nuclear physics, we're going to learn a lot about particle physics, about fundamental particles, about the information that comes from neutrinos, from cosmic rays, and we're going to be able to weave together. So the future is really weaving together all these different pictures that are brought to us by various messengers to get a more holistic picture of the universe as a whole.
So what's roughly the timescale for all of this to unfold with LIGO India? When are we expecting it to join the global network of detectors?
Right. So the current plan is that LIGO India should start functioning in 2025. And that is a good plan, and that in the sense that that will be a good time, because by then it is true that we will have a lot of events already with the existing detectors, especially with the next phase of advanced LIGO A+ that we will have, the next enhancement that we will have. But still, there will be still a lot of science to be done. And as you pointed out before, LIGO India will still be in a position to localize the sources much better.
Yes.
And therefore follow, observe the universe then, point the telescopes at an appropriate place, also look for neutrinos and such things from that patch of the sky. So one is going to get much more information about the universe by then.
Yeah.
But at the same token, I must say that it really is vital, absolutely vital, that there are no delays. If there are substantial delays, then the potential of LIGO India would diminish rapidly, because by then a lot of science would already have been done.
Yes.
And that would be a real pity. So I do hope that, the policymakers are very wise, they provided this funding, everything happened, but there are always practical constraints. But I do hope that the leadership will see to it that they really stick to this timetable and get LIGO India into the circuit by 2025. That is vital, that is absolutely important.
Well, let's hope that that is indeed the case, and that means the next decade is going to be truly exciting. And we have already achieved so much in this 100 years since Einstein first proposed the theory of general relativity, but it looks to me as if this new field of gravitational wave astrophysics has a very bright future.
Exactly. I think we're going to learn new things about the universe, things about which we did not even suspect. Right?
Yes.
That is really the best thing of it all.
Yes, exactly. Well, that sounds like a great point to finish. Thank you very much.
Thank you.
And we look forward to this bright future with the unexpected just waiting round the corner.
Absolutely. It's a pleasure.
Thank you.